Hi students, let's continue with the moment of inertia. So we have been finding moment of inertia of few continuous masses using integration. Now for the ones who don't love integrating so much, this is a good section. We don't have to do integration now. We are still going to find moment of inertia, but then we have already integrated, or somebody has integrated for us, and we know the moment of inertia of a certain body about a certain axis, and we are going to find the moment of inertia of the same body about some other axis. So we are going to deal with two theorems. One is parallel axis theorem and the other one is perpendicular axis theorem. So in this particular section, the first part of this video, we'll be doing parallel axis theorem. Now what is this parallel axis theorem about? It tells you the moment of inertia of any body, say this is any body, about any axis. I'll call this axis as PP dash. The moment of inertia of this body about this axis, say IP. Now it tells you what would be the moment of inertia about this axis provided you know the moment of inertia of the body about a parallel axis shifted parallelly shifted from PP dash to through the CM, and I'll call it as ICM, which is in fact parallel to PP dash. Now I'll again emphasize that you have infinite number of axes going through the center of mass, one being like the perpendicular outside and inside the board, one being this way, one being that way. There are so many axes going from the center of mass. But if you need to know what is the moment of inertia about a certain axis, you need to know the moment of inertia of an axis which is parallel to the first one. So that's the criteria over here. It has to be parallel to the first one. And if you know the moment of inertia about the center of mass, which is parallel to the axis what we are going to find, then the theorem says that IPP dash would be equal to, I'll call it as IP, would be equal to ICM plus or minus something. What do you think? It would be plus something, because I think I have already told you in the first lecture why the ICM is always the minimum. ICM has the minimum value of the moment of inertia compared to any other axis which is parallel to it, So any other axis which is parallel will have a value little more than ICM. ICM plus md square. Now what is this md square? M is the total mass of the body, say concentrated over here. Since I'll prove it also, so I'll use capital M over there, because small m I'll be using for all distribution of masses. So say capital M is the mass of the body, the net mass of the body is capital M, and the distance between the two parallel axes is d. Suppose the distance between the two parallel axes is d, then md square has to be added. So mind you, the shifting can happen. The axis has been shifted only from the CM. Suppose you know the I through some other axis and you shift parallelly, then this formula is not going to work. This formula is only going to work when moment of inertia of the CM is involved, and I will quickly prove it to you. And the proof is as such not necessary, but what the proving will do is it will reinforce in your head that you have to use a parallel axis theorem with this ICM getting involved and not any other random parallel axis. So and in fact I'll do a very simple proof so that we can just get the essence of the proof and get over it. So I'll not take a 3D body, I'll just take a 2D body and do the proving for you. So maybe over here I'll do the proving. So suppose you have a mass having these point discrete masses, many of them. Say this is your M1, this is M2, that's M3, and so forth. Okay, it's a rigid body, it's a single rigid body, so I've connected with a massless rod for reference, and I want to know what is the moment of inertia of this thing about this axis and I know the CM is somewhere over here. Mind you, many a times you will have to figure out where is the CM so that you will be applying the formula correctly. So most of the cases you should be knowing where the CM is, or you will be required to find out where the CM is. Anyways, coming back to this, say this is your CM, center of mass, and we have axis which is, we'll use the same denotions. So again d away, and all these masses added is capital M. So your capital M, where shall I write? Capital M is summation of all these masses, M1 plus M2 plus M3, M1 plus M2 plus dot 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 is your capital M. Now if I had to find the moment of inertia IP, what I had to do? I had to take distances from this PP dash axis and do a mx square for each and every body and add up the mx squares of each, because mx square would be the moment of inertia of each tiny point mass, and the sum of that will be the moment of inertia of the whole thing. And then if I have to find out the moment of inertia about this, I have to do a mx square from that distance, and we'll see how they are related, why it is coming like this. It's a simple mathematical certainty that this is going to happen. There was an interruption. So what was I saying? You have to find the center of mass of this body, and with respect to, say, this axis. So how far is the center of mass? So I hope you remember that for doing that we should know the distances of each mass from the axis from where we are trying to find. So I'll call those distances as, say, x1, x2, and x3, one being on the other side. So we'll serve as an example. Anyways, so what we'll do to get the center of mass is m1 x1 plus m2 x2 plus m3 x3 plus dot 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 is equal to, or divided by the total mass, which I have written as capital M, is equal to d. So I'll just write it as m times d. Moment of all the masses across this axis is the moment of the whole mass as if concentrated at the CM about the same axis. So that was the essence of getting your center of mass. So this we'll have to utilize somewhere, because after all we have to prove that this theorem works only with the center of mass. Now suppose I had to find my ICM and IP. So what will I do? So any one I'll write first. So let me write IP first. So what we have, our IP as moment of inertia about this as m1 x1 square, m2 x2 square, m3 x3 square, dot 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 dot. That's your IP. Okay, and what's your ICM? So I'll just write the ICM over here because I think I'll require more space. So your ICM would be equal to, let me use the same variables so that we can ultimately prove. So your ICM would be equal to all the mass into the distance square from this axis, from the center of mass axis, which is parallel to that. So what is this distance? How much is this much? What do you think is this much? That's your d, and that's your x1. So how much is that? That's your d minus x1. Similarly, how much is this? How much is m3 away? That was your x3. That's your d. So it is x3 minus d. So anyways, it doesn't matter we write d minus x3 or x3 minus d, because ultimately we have to do a square of it. So thankfully it will not bother us in our calculations at all. So what we have is m1 from the central axis is d minus x1 away and a square of it. Okay, then your m2, it could be any distribution. Your m3 can be this side, that side. Ultimately the maths is going to work in the same way. So m2 into d minus x2 the whole square, m3 into d minus x3, you may write it as x3 minus d the whole square. It's the whole square, so it will not matter. And just to have it in the same format and a certain sequence, so I'm writing it like this. So what we get is ICM. Somehow I have to bring this IP into picture. So what I'll do is I'll just open the d minus x1 whole square and write it as x1 square plus d square minus 2x1 d. So if I take x1 square from here, x2 square from there, x3 square from there, so what do I get? I get m1 x1 square plus m2 x2 square plus m3 x3 square and so forth, plus what I'll have is all the d squares will come. So what do I write? m1 d square, m2 d square, m3 d square, dot 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 dot. So you can see that we can take d square common and we get m1 plus m2 plus m3, and this guy is already IP. That was your IP. So what we are getting is IP plus total md square, which is not the theorem at all. It is IP minus md square. So hopefully we'll get other things which is going to land us there, and we are yet to use this. That where was the CM? This tells you, this equation tells you where was the CM. In physics, you should have a sense of what equation is leading you where. So what equation has to be used, has to be applied. So that sense is going to help you in physics. So anyways, what's the third term over here? From maths, the third term is minus 2 m1 xd, then m2 x2d, then m3 x3d. First one is m1 x1d. So there's a 2 which is common, and d is also common to all of them. So without writing it in two steps, I'll just write it in one step. 2 is common to all of them, d is common to all of them, and then we'll have a minus is common to all of them. So minus 2d I have taken out. m1 x1 plus m2 x2 plus m3 x3. I hope you see where it is leading to. So we have these three terms. Okay, so I'll just put a equal to in front of it. So what is this first term? That's your IP, your m1 x1 square, m1 x1 square, m2 x2 square, m3 x3 square. That's your IP. That has to be the moment of inertia about this if you were finding using the basics. So that's your IP. What's this line? D square common, m1 plus m2 plus m3, and m1 plus m2 plus m3 is nothing but the total mass m. So that is a m d square. That's your next line. So this line gives you that. Okay. Now what is this line? Minus 2d m1 x1, m2 x2, m3 x3. So thankfully we can make use of this. That's your m1 x1, m2 x2, m3 x3. So what is that? That's md. So md. So minus 2d into md. So what does it give? It gives minus 2md square. Yeah, so what was plus now becomes minus. So what do we get? I'll just put it over here. What we get is, we get ICM is equal to IP minus md square plus md square minus 2md square. So leaves me with minus md square. So that's your parallel access theorem. Okay, now this was a very simplified proof, but just to give you a sense that how it can be. It's a mathematical certainty what we are getting, and that mathematical certainty is coming from the fact that we are using this. We are using this thing, that is, we are using that a center of mass has been shifted, otherwise it would have not happened. Now you can do it in 3D also, have all these x1 x2s as vectors, x1 vector, x2 vector, x3 vector, and still it is going to work in the same way. So but don't bother about it. The point is, just remember that ICM among all the parallel axes is the least, and you have to add up something. So this is in fact a kind of proof why ICM is least, because if you go parallelly away, then whatever will come will be a plus m and a d square. That's a positive quantity, so plus a positive quantity. So it's a mathematical proof why ICM is the least among all. So that's the theory. Let us do a couple of questions on it so that you get a hang of it. So first one, I'll give you a very simple one. And before I give you a question, let me just increase your faith in the formula, because you already know that for a rod, the moment of inertia about cm, ICM, and that way, not this way. This way will be almost zero if it is a thin rod. ICM is 1 by 12 ml square, where m is the mass of the rod and L is the length of the rod. And about this axis, which is parallelly shifted, it is I some axis, say about, let this point be, okay, again P. So IP is equal to 1 by 3 ml square. Can we just implement this formula to cross verify it? Let us just do that. So what do we get? IP is equal to ICM plus MD square, where D is the shift of the center of mass from the parallel axis. So ICM over here, this parallelly over there, is 1 by 12 ml square plus m. What is the shift? How much is the shift? This much is the shift. That's L by 2. L by 2 is the shift. So your D is L by 2. So L by 2 whole square over there. Yeah. So what do you get? What do you get? You have ml square in both of it. So you have 1 by 12 and that's 1 by 4. So you can take 1 by 12 as the LCM and you'll get a 1 by 12 over here, and instead of 1 by 4 you can write it as 3 by 12 ml square. So you get a 4 by 12, which is nothing but 1 by 3. So this is what you get. So I hope this restores, or I'm sorry, not restores, I hope it brings faith to this formula. You have a stronger belief in this formula, I hope, with this. So anyways, this formula works for sure, and I'm going to give you a couple of questions. One, a very easy one, and the next one, maybe some work we'll have to do in that one. So the question is over here. Easy question. Suppose you have a ring which is having a lot of beads on it. Let's have 12 of them, like a clock, all symmetric. So the total mass, all beads are having the same mass, all blue dots are having the same mass, the red ring is having a certain mass, and the total mass is m, and radius is, say, r. R is the radius, mass is m. Now the question is, I'll make the question very simple. I was planning to do it through one of the beads and then you find out where's the distance and all, but we don't want to do any geometry. I just want you to apply the formula correctly. So I'll make axis in the same plane. These beads are having hardly any 3 dimensions to it. They are almost like point masses. Okay, and I know the moment of inertia through this axis, I'll call it as axis 1, and then moment of inertia 1 I know, I1 I know, and what I need to find is moment of inertia about another axis which is r by 2 above the center. So the first one was tangential and the other one is r by 2 above the center. Will that axis go through the bead? So yeah, it will go through the bead. So I was initially asking you to find through the bead which will be r by 2. How do you get that r by 2? That bead will be 30 degree above, because all these are 30 degree apart, this being 90 degree. So that is a r sine 30. R is the radius, r sine 30 would be the height. If I make, so r sine 30 is going to give you r by 2, So what I need to find is I1 is given to you, I2 about this axis is how much? That I2 is a parallel axis which is shifted from I1. So do it in quick time. Pause the video. Okay, so I hope you did not fall for the catch over here and not write I2 as I1 plus or minus whatever M, I'm sorry, capital M was given as a mass, so capital M into distance between the two parallel axes. Distance between the two parallel axes is R by 2 square. This would be absolutely wrong. I hope you know why that would be wrong, because we can't have the parallel axis theorem going around without the center of mass ICM involved. So neither I1 was ICM nor I2 was ICM. So if any one was ICM, the other one would have been ICM plus the MD square. So over here, first I have to get my ICM. So what is our ICM? That is this axis. ICM, that is what you have to get. So how will you get that? I1 is given to you. So what you'll say is the relation between I1 and ICM is this, is mass and the distance square. So what is the ICM and I1 distance? What is the distance between ICM and I1? That's R. So mr square. I1 is given to you, ICM was not given to you, R is given to you, M is given to you, M is given, R is given. So what you have is, you have your ICM. So from this equation, equation number 1 you may call it, you get your ICM, which is I1 minus mr square. Then we have to find I2. So what will be your I2? I2 will be equal to ICM, applying the parallel axis theorem. It is I2 is from ICM a certain amount more. How much is that? M into distance between ICM and I2 axis. So what is ICM and I2 axis distance? That is R by 2 distance. So that's square. So but we didn't know the ICM value earlier. Using equation number 1 we have found out. So you can substitute that value of equation 1 in equation 2 to get the answer. So what we get is, your ICM would be I1 minus mr square from equation 1, mr square, and this plus mr square by 4 remains. So ultimately what we see is, you have I2 equal to I1 minus 1 plus 1 by 4 will give you minus of 3 by 4, minus 4 by 4 plus 1 by 4, mr square. So that's your answer to this question. So I hope none of you fell for the catch and did this. So this is to again emphasize that you have to hop on to ICM first if it is not given, and then go anywhere. So if I ask you what is the moment of inertia about this axis, you can't go from here to there directly. You have to go to ICM, get that value, and then go beyond. So you have to use ICM. Okay, so I'll just clear the board and give you the next question. Gear up for that.